Good morning. We will start a new chapter, that is chapter number 6, and it's about electromagnetic induction. Here will be studied about Faraday's experiment and how an EMF is induced when we have an alternating magnetic field. And also we'll learn about magnetic flux and the direction of induced EMF, and then two important concepts, that is self-induction and mutual induction. Also we'll use this principle in AC generator. So before starting Faraday's law, first we'll see what is magnetic flux. So in simple, I have written a definition here. So before that, I'll tell you in simple, a magnetic flux is a measure of magnetic lines of force in a magnetic field. For example, it is just measuring the number of lines. So we know the magnetic field is represented by these lines. So field lines, or it is also known as lines of force. Lines of force or magnetic field lines. The magnetic field is represented by these arrows. So if you have a given surface, the magnetic flux, it's a measure of these field lines, or the number of magnetic lines of force in a magnetic field. Now here I have shown it as 2, so like that there will be number of field lines. The total number of magnetic field lines will represent the magnetic flux. So this is a simple way of explanation, but when we come to the definition, we have to write it properly. So magnetic flux, we can say that it is a measure of the amount of magnetic field passing through a given surface. So it is always measured with respect to a given surface. How many number of lines cross that surface? That is the magnetic flux. It's a measure of how many field lines passing through that given surface. And mathematically it can be measured as the surface integral of the normal component of the magnetic field passing through that surface. I'll explain this second term, how you can calculate this. Before that, we know now, so the magnetic flux linked through a surface is the number of magnetic field lines cutting through the surface. Hope you understood what is the definition of magnetic flux. Next we will see like how we can measure this using mathematical formula. Here I said the flux is measured as the surface integral of the normal component of the magnetic field passing through that surface. So what is the normal component of the magnetic field? Now see this figure. This is the given surface, and this vector is the area vector, normal to area, or the area vector is a vector which is drawn perpendicular to the area of the given surface, like this, area vector. Now you have this magnetic field. So to calculate the magnetic flux, you have to take all the field components which are parallel to this area, or perpendicular to the surface, because that is how the definition says. The magnetic flux is measured as the surface integral of the normal component of the magnetic field. The normal component of the magnetic field through a surface. So it is given by the surface integral of B dot ds. Is measured as the surface integral of the normal component of the magnetic field. Now here we have a slanting magnetic field B. You can resolve it into two components. One is along the horizontal direction, like this. I'll show here. One will be along the horizontal direction, another one will be along the vertical direction. So this vertical component is, from this it is B cos theta, and this is B sin theta. So we want only the components which are perpendicular to the area of the given surface. It is a measure of the surface integral of normal component of the magnetic field passing through that surface. If you have a slanting magnetic field, convert this field into two components, one along the horizontal direction, another one along the vertical direction. Now the component along the vertical direction, which is the component perpendicular to the area of the given surface. Therefore it is calculated as surface integral of B dot ds. In case if the area of the surface is A, then we can write this equation as B dot, because in case of uniform magnetic field, into ds dot, and let us say the surface integral of this surface or the area of the surface as A, as in the given figure. This equation will become B dot A, or it can be written as BA cos theta. This is magnetic flux. Now the magnetic flux is represented by phi. Magnetic flux is symbolically represented by phi. Therefore we have phi is BA cos theta. Phi is BA cos theta, and its SI unit is Weber. SI unit. Weber, and its WB. Phi is always represented by Weber. Now you got it. The magnetic flux is a measure of field lines passing through the given surface. It is measured as the surface integral of magnetic flux or field lines cutting through the surface normally. And finally we got the equation BA cos theta. Now we can consider different cases, like if the field lines are parallel to the surface, what happens, what will be the flux, and when do we get maximum flux, when do we get minimum flux. So we'll take different cases. First one, if the magnetic field over the entire surface is uniform. That we have already discussed that case, but I'll tell you again. If the magnetic field over the entire surface is uniform, and let's say we have, so this figure only you can consider in that case, this figure. So in case of uniform magnetic field only we got this equation, because that time we took area as A, BA cos theta. If the magnetic field over the entire surface is uniform, then phi is BA cos theta. BA cos theta. Pictorially also you can represent. Here say the field is going like this, and then we have area vector like this, because it is normal to the surface, and this is theta, and this vector, the B component perpendicular to the area, that is BA cos theta. B is the magnetic field and A is the area vector of the surface. Now if the magnetic field lines are parallel to the surface, then what will happen? If the field lines or magnetic field lines are parallel to the surface, then the magnetic flux becomes is BA cos theta, which will become, now calculate what is theta. Now see, this is the area and we will have area vector like this. Let us say all the field lines are parallel to the surface. Now the vertical component or the component perpendicular to the area is 0, or here the angle between A and B is 90 degree. Therefore BA cos 90 and flux becomes 0. That means actually there is no flux which is cutting through the given surface. If the magnetic field is parallel to the surface, then there are no field lines which are cutting through the given surface. Therefore flux is 0. Now the third case is, in this case the magnetic flux is minimum. So flux is minimum or 0. The flux becomes minimum or 0 when the field lines are parallel to the surface. Now in the case of field lines, when the field lines are perpendicular to the plane, like for example we will write when the magnetic field is normal to the plane. Magnetic field B is normal to the plane. This is the case, we can represent it like this. Now let us say the magnetic fields are cutting through the surface B, and area vector is the vector which is drawn perpendicular to the given area. Now here angle between B and A is 0. The flux phi is BA cos 0. Cos 0 is 1. It is BA. Flux is maximum. Magnetic flux is maximum. The magnetic flux becomes maximum when the field lines are perpendicular to the given surface area. Remember the unit is Weber. Flux is BA cos theta. The important equation to remember is flux is BA cos theta. Theta is the angle between B and A, and this is important and we will be using it in further our discussion.